Today I'd like to talk to you about ultraviolet spectroscopy. We're going to look at theory, and then we're going to talk about a specific experiment that we're going to do. So we are all familiar with the electromagnetic spectrum. And it turns out that this little sliver here is the visible part of our electromagnetic spectrum. Right? And the colors range from red, right, to orange, to yellow, to green, right, to blue, kind of this indigo color, right, and then violet. And that's your Roy G. Biv of a rainbow, right? And we're going to be looking at UV-VIS, so this near ultraviolet part, somewhere around right here-ish or so, all the way up to about 800 nanometers is the section that we're going to be looking at. Now, in our experiment that we're going to do, we'll provide this data to you, or we'll carry out in our lab. We're going to be looking at the ultraviolet spectra of acetone, and we're going to be doing that in two different solvents. We're going to be first looking at a nonpolar solvent like cyclohexane. Right? Sometimes we actually will use hexane, but both of those are nonpolar. So that's going to be our first set of data. We'll get a UV-VIS spectrum of that. And then we'll take a look at acetone in something that has hydrogen bonding. So ethanol is one of our common choices, right? Sometimes we might actually use water here too, depending on what we want to do in that part of the experiment. But in any case, we're doing a nonpolar versus a polar solvent. Now, there are some calculations that we're going to do in this experiment, and we have to review some of those numbers that we've seen before from physics and from general chemistry. So we know that frequency is equal to hertz, which is 1 over seconds. Right? We also know that lambda here is our wavelength, and it's measured in nanometers, centimeters, meters, whatever. And frequency and wavelength are related to each other by inversely by taking the speed of light and dividing it by our wavelength. That gives us our frequency. Now, the other thing that we have seen before, we've seen this before when we talked about infrared spectroscopy, and that is wave numbers. So remember, wave numbers are equal to inverse wavelengths, right? So centimeters to the -1, or whatever the wavelength is. It could be nanometers to the -1, so on and so forth. So all of that can be related to our delta E. And our delta E is hc over lambda, or hc times our wave number here. And of course, this is also equal to h times our frequency, right? Since our frequency is equal to this, that's the other relationship that we get there. So we're going to do some calculations, and you'll actually go through and you're going to calculate this delta E based on some interesting observations that we can get from, and some data that we can get from our UV-VIS spectrum. Now, I want to point out here to you also that there's an inverse relationship between wavelength and our energy. So we're going to be looking at this delta E, that's our energy difference, and we're going to be able to get this wavelength, this lambda. Lambda max is going to be obtained from our UV-VIS spectrum. Right? And just so that we all have the same numbers and we're getting not caught up in sig fig issues for things like mastering and stuff like that, mastering chemistry, let's all use the Planck constant 6.626, right? And the speed of light we'll treat as 2.997 times 10 to the 8 meters per second. Now, what we're going to be looking at once we provide to you data for these UV-VIS spectrum is we're going to be finding the lambda max. So often what you get is you get this little curve where it comes up to this top high peak and plateaus down and trails off, and down to this kind of baseline. So here is our absorbance here, okay, and down here is our wavelength. So then we tiptoe along and we look up this thing and we find the maximum absorbance. So that's your maximum absorbance, and that wavelength there is called your Lambda Max. So that's the number that we're going to be looking at. Now with that Lambda Max, we can go through and we can calculate delta E's, right? And that's what we want to be trying to find. Now the other thing that we're going to calculate is molar absorptivity. So we'll do that using Beer's law. So the A in Beer's law is obtained from the spectra. That's your absorbance, right? C is your concentration. So we're going to have, for concentration, we're going to have, right, some volume of acetone, right, in hexane. If we know those volumes, then we can calculate what the molarity is, right? L is the path length of the cell. So this is your cuvette. That's typically going to be 1 centimeter. So it's not important numerically for us. And then this epsilon down here below, that's the thing that we're going to be calculating, which is our absorptivity. Okay? So let's take a look here. Now, in UV-VIS spectroscopy, electrons are excited from lower energy levels to higher energy levels. So remember, we have this sigma bonding, we have pi bonding. This is your non-bonding line here, so things like lone pairs, for example. You have anti-bonding, pi, right, and sigma anti-bonding up here at the top. Now, generally speaking, electrons are excited from the highest occupied molecular orbital. Remember, that's your HOMO. Usually that's sigma in or pi, one of the three of these things, to the lowest unoccupied molecular orbital, or your LUMO. It's usually your sigma star or your pi star. All right, now let's talk first, before we look at carbonyls, let's talk about the UV-VIS of just alkenes. So let's go through this page a little bit here. So alkenes and non-conjugated dienes, they have absorptions below 200 nanometers. So that they fall in an area that typically is not part of the visible spectrum. And that's because the energy difference between the HOMO and the LUMO is large. So remember, a large delta E means a smaller, right, wavelength there. Okay. Now in conjugated dienes, those energy levels between the HOMO and LUMO are much closer to each other, and because of that, the wavelengths of the absorption are longer than 200 nanometers. And remember that 200 to 800, right, is your UV-VIS region, right? So that is the target area that we're trying to get into if we want to see color. Right, so here, a smaller delta E, right, between your HOMO and your LUMO gives you a higher wavelength. Now, UV-VIS spectroscopy is usually introduced in organic chemistry in the chapter that discusses conjugated dienes. So you're looking at 1,2 and 1,4 addition and things like Diels-Alder reactions, right? So if we take a look down here below at these two cases, so here's ethene. So ethene, of course, is just CH2, CH2. So it has a lambda max at 171 nanometers. So down here below, here is our ethene. Okay? And here's your highest occupied molecular orbital to your lowest unoccupied molecular orbital, and here is your delta E for that, right? So energy would come in, and then you'd have an electron being kind of excited up here to this higher energy state, right? Okay. Now if we take kind of two ethylenes and we stick them together, you get 1,3, right, butadiene. So when you do that, that delta E gets smaller. So here, that delta E that we have is a smaller number, right, than this delta E that we see right here. Now the trend here is that the longer the conjugated system, the smaller the energy difference between that HOMO and the LUMO gap. So we can see that same principle as we saw on the previous page with this diagram also. So here's your ethylene, right, your delta E, right? If you put two ethylenes together in a sense and get 1,3 butadiene, then your delta E just gets a little bit smaller there, right? So that's going to give you a larger wavelength as compared to this number down here. Now, if we can get that 217 to become larger and fall somewhere between 400, right, and 800 nanometers, then we can start to perceive color there. Let's take a second and let's talk about color. So there's three basic ways that we perceive color. So here's our color wheel, starting off with our red up here, right, orange, yellow, green, blue, and your violet or your purple here, right? So we perceive color first either by emitted light. So when light is emitted from a lamp, for example, or from something glowing, we observe the color that corresponds to the emitted wavelength. For example, a light source that emits at 580 appears yellow. So 580 is right somewhere around right here or so. So we see a yellow color. Now the other thing that we can see is we can of course see the color of objects that are not glowing. They can reflect light to us. So when we observe the color of an object, right, that's not glowing or emitting light, we are not observing that emitted light. Right? So of course a carrot is orange, but not because it's glowing orange. If you turn the light off, there's no color there anymore, right? Instead, we observe the color of the light that's being reflected back to us. So the color that our eye perceives, in fact, is not due to that wavelength of light being absorbed, but rather the complementary color that's produced by that absorption. So if you look down here below, we have color of light that's being absorbed, right, the wavelength of light down here. So violet about 400, right, blue 450, right, then we have these ranges, right, yellow, orange, red, and red, so on and so forth. So that's the color of light that's being absorbed. If a blue is being absorbed, then the color perceived as being orange for that. So beta carotene, looking down here below, that's the pigment from carrots. So the lambda max of that is 452. Right, so it's absorbing at 452. So we come up here, that's right here. That's in that blue region. So it's absorbing that color, but we perceive it as being orange. Right, malachite green, that's a triphenyl methane dye. So that absorbs at 617 nanometers. So you come over here, absorbing 617. So you see a green color, a blue-green color to it. Now the other thing that we can see is we can see light because of transmission. So when looking at a transparent object, for example, or solutions, the eye perceives the light that's transmitted. Right? Just as before, it is the complementary color of that light that is actually perceived. Now, one thing that we're going to see for our experiment now, so this is kind of specific to our carbonyl experiment, is that there are transitions that are involved for the carbonyl compound. There's two transitions that are seen here. So we have this transition that's called the allowed transition. Right, so you have your epsilons at 5,000 to 200,000 here, and that's your pi to pi star. Right, so this is just a depiction of showing those electrons moving from a lower energy state to a higher energy state. And then we have the forbidden ones. Right, so the forbidden transitions are 10 to 200 nanometers. Now that forbidden transition refers to something that that you'll talk about later on if you're a chemistry major when you get into quantum chemistry a little bit. Okay. Now, the solvent also is going to affect our lambda max. So, right, of course, if we have here a solvent in which we can carry out and have hydrogen bonding, that H bonding will affect the energy levels of our transitions. So what we're going to be looking at in our experiment is this N to pi star. So what we want to look at is the effect of increasing solvent polarity on these carbonyl spectra. So the idea is that we're going to take something that's nonpolar and we're going to compare it to something that has hydrogen bonding. So remember that N to pi star, that forbidden transition, that's the one that we're going to be examining in our particular experiment here. So remember that this is our delta E here. Okay, and then when we add a solvent with H bonding, for example, water or ethanol, it causes our N to become lower. So what that does here is that increases our delta E. Right, so then we have an electron promotion. So you have your pi star, you have your N down here, and we see an electron promotion. Right, so again, what that does, right, is it increases our delta E, which decreases our lambda. Okay, so let's see how that affects things when we start looking at our data. The other thing is that the pi to pi star changes too. Now, we're not going to be looking at this specifically for our experiment, but it turns out that when we add that solvent with H bonding, both the pi and the pi star are decreased, but they don't decrease by the same amount of energy. The effect is greater for the excited state. So here we have our delta E, right, without any hydrogen bonding, and with H bonding, that delta E gets smaller. That smaller delta E means that we have a larger lambda for our experiment. So again, what we're going to provide to you is some data for the UV-VIS spectrum of acetone in ethanol or water, and we're going to compare that to acetone in cyclohexane or hexane, right, a nonpolar solvent. And from that data, we're going to get our Lambda Max and our absorption. We're going to be able to go through and calculate our concentration and get our molar absorptivity, and we'll be able to do some interesting calculations that involve the energy involved in hydrogen bonding.